Hello, everyone. Today, let's solve the question 1483, case ancestor of tree node. This is the question that specifically asks you to use the technique called binary lifting, and which is kind of the dynamic programming that allow you to access um, 2 to the power of n parents really quickly in an O log n time. So let's jump right into the code. So this is initialization of binary lifting. And what is the most important thing is this ancestors. So this is the two-dimensional DP. So you access like this. And the first input is going to be the node. So in this case, we are going to have like zero index space node. So 0, 1, 2, 3, 4, 5, 6. So this is going to be the integer, and this zero represents the exponents of this the nodes of parents. So let's see if the exponent is zero, that means 2 to the power of zero, which means it's equal to one. So it's just a normal parents. And what if it's one? If it's one, exponent is one, so it's going to be two. So this is going to be grandparents of this, let's say six. So the two would be the parents, and then zero would be the grandparents. So it's so when it comes to the six nodes, when the node is six, when it's zero, it should be two, and if it's one, it should be zero as a node. So that's how you cache it. The problem is like how you can cache it. So, but first of all, let's think about how many like exponent can be used in the tree. So if you think about it, tree is always O log n, and in this particular example, it's a binary tree. So you can simply take this mass.log n2, which is just the mass log function in the Python, and you convert it into integer. And then this is going to be actually this is sale. So not wrap it as like floor, but you want to increment to the next integer if you have any smaller number than one. Okay, so that is going to the max exponents. So in this case, let's see, we have six nodes. So what is the six, and when you take six with the two, that is going to be how much is that? 2 point something. So it's going to be three. So the height is going to be three, right? So okay. So now we get this max exponent, and let's go through like how you can initialize this self-built ancestors. So first you think so first let's fill out the case of zero. So like the normal parents, you just put like so in this particular example, we have parents as a parameters, and then you just want to get the case ancestors of tree nodes. So you can simply use this parents as to inserting the parents in this ancestors. So for every node, you iterate over every node and then put the nodes here and then parents here so that it can be filled out for zero case, parents case. And what is the next case? So the next, like the base case is when ancestor, I mean the node is zero. So which means the root node. When you at the root node, there's no parents, obviously. So anything that you put here, even this is zero, that means like the parents of root node, it doesn't make any sense. So I am going to put -1 as like a default value, which represent like this is invalid, okay? So this is the kind of the base case. And after that, this code is actual like initialization for all the ancestors and all the nodes and all the exponents. So let's see this code. And first of all, I want you to pay attention. We are going to iterate this exponent first, not the node first. And the reason because, so let's see this case. So what I'm doing here, so I'm taking, so the previous exponent, current exponent minus one of the node. So I'm taking a look at, so you're at here, so you're checking current minus one. So this is going to be the prep, okay? But you want to get, actually, what do you want? What do you want is something like this, right? And how to retrieve this data based on something what we already calculated. So you think about it, you're already at this much like parents. You proceed to the like this much to the power of current minus one. And then so you're halfway. So let's think about it. From six. So let's say you want to calculate zero. But the actual this so current should be two because the height is two, but you're going to minus one, so it's going to calculate. It's going to give you this two as a prep. And if you take, the same step from two to zero, that is going to be like two to the power of current exponents. Does it make sense? So you're already here. Okay, so it's kind of like this. Current minus one, right? And then you're going to take this prep, prep, and okay, so let me see. You're going to take the one more step for prep to the power of current n minus two. So you proceed this much step, that is going to be, if that makes sense. So this is going to be like this, actually. And yep, and represent two to the power brand, two to the power of current. So you already jump the half of the steps from six to two. So if you take another half of the step from prep to, that is going to be what you want, like this exponents from this node. So if the prep is no minus one, which means it's not invalid, it's valid when when it's valid, you're going to be check the prep and then exponent minus one, and that going to take you to zero. So that's how you fill up all the node and exponents. And because we want to access this exponent minus one, we want to calculate first, um, exponent minus one first. It is doable if you for loop with exponents first and then node later, because like so let's say this exponent is zero, it goes through all the nodes, and when it's zero, obviously this exponent is going to be minus one. It doesn't make any sense. So when exponent is one, um, so this is going to be zero, and then zero, we already calculated in the first for loop, so it's you can utilize the values in this logic. So that's how you fill out this self-ancestors dynamic programming memorization. So let's go to how you can utilize this ancestor mapping. Memorization to calculate the case ancestor very quickly. So there are several ways to do this, and obviously, this is not actually the most efficient way. to solve this question, but I believe this is more intuitive and it's easy to understand. So let me go through this um, logic first. So I'm converting this k to the binary 0101. This is just a Python technique, Python built-in function to convert this k um, to binary representation. And I'm going to follow with this binary and the exponents. So in what I'm doing here, let's say, so now the k is like this, right? Now k is like this. And I want to know like how much exponent that we're looking at now. So obviously this is the case like this is 2 to the power of 0 and this is 2 to the power of 1, right? And this is 2 to the power of 2, this is 2 to the power of 3. So we have I as 0 at the first, this one, this is going to be 0 as an index, and this is 1, this is 2, and this is 3. So it's kind of the backwards of the exponents in this I. So I'm going to subtract in I plus 1 from the length of binary, and that's how you get the exponents here. So after that, if the bit is 1, which means that we have the binary, the bits in this exponents, we want to jump like up to the, this much exponents parents. So I'm going to utilize this map and then retrieve the new nodes, like parents nodes, and more parents nodes, and then check if it's invalid. And if it's invalid, you can just simply return -1. And otherwise, you keep making this logic happens until um, like all the way to the end, and then finally return the nodes. So let's run this code really quickly. Okay, so as you can see, it's a pretty efficient solution. Yep. And this is extremely useful technique. And this is obviously kind of the question that asks you to just build the binary thing. But there's so many use cases and patterns that you could utilize this technique to many problems. So I hope you understand the core of this technique and then, take advantage of it and then apply it to more harder question because this is a really harder question, but there are many other harder question out there that is required binary rifting technique. So today, that's it for today. So thank you for watching. I'll see you in the next video. See you.